Hey class, today I will be teaching you about neural architecture search, or NAS for short, and why you should care about it. This is going to be a high-level overview, so it will help to have some background on neural networks, but we won't dive into anything too technical today. First, let's talk about some of the motivation behind neural architecture search. Say you're a doctor and you use medical imaging to diagnose patients with lung cancer. You've heard the buzz around AI and are wondering if you can use machine learning to help you with your diagnosis. Just one problem. You notice that all of the top models are designed by AI experts. And while you are a medical expert, you are not an AI expert. So, how can you choose the best neural architecture design to help you diagnose lung cancer? Traditionally, neural architectures are hand-designed, requiring human expertise in neural networks. With neural architecture search, or NAS, instead of a human designing the architecture, you now have an architecture that is generated by an algorithm. Then, for people like doctors who want to use neural networks but aren't neural network experts, it becomes easier to find a good neural architecture design. Let's go over a few paradigms in neural architecture search. We have reinforcement learning, neuroevolution, differentiable architecture search, or DARTs for short, one-shot NAS, and training-free methods. I'll just give a brief overview of each of these methods without going into too many technical details. The reinforcement learning approach can be summarized pretty well by this diagram. The controller, which is a recurrent neural network, generates neural architectures. The child architecture is then trained, and its validation accuracy is taken as the reward. Then, the controller takes this information to update how it generates architectures, and this repeats over many iterations. Whereas reinforcement learning takes a gradient-based approach, neuroevolution uses evolutionary algorithms to generate architectures. We have a starting population of neural architectures that mutates and evolves over time according to simulated natural selection. The set of possible edge operations for a neural network is discrete, meaning the space is non-differentiable. Differentiable architecture search, or DARTs for short, applies a process called continuous relaxation, which makes the search space differentiable, allowing for gradient descent. The previous methods can be expensive because they involve training the candidate architectures in order to evaluate their performance. On the other hand, one-shot NAS trains a large super network, and the candidate architectures are sub-architectures of the super network, containing only some of the components of the larger supernet. This way, you only have to train one super network as opposed to many candidate networks. Even faster than one-shot NAS is training-free methods, which require no training at all. This works by coming up with some sort of heuristic for the pre-trained architecture that correlates with validation accuracy. Then, you can predict how the architecture will do without ever training it. To recap, some popular paradigms in neural architecture search are reinforcement learning, neuroevolution, DARTs, one-shot NAS, and training-free methods, with reinforcement learning, neuroevolution, and DARTs being more expensive, and one-shot NAS and training-free methods being less expensive. Unfortunately, there have been some reproducibility issues with NAS. Zoff and Lay's reinforcement learning approach, which sort of generated all this recent hype around NAS, took 800 GPUs running for 28 days. I mean, 800 GPUs can't be that bad, right? How much does a GPU cost? Okay, let's look at the cheapest one, which is $249. And we have 800 GPUs, so that is $199,200. Yeah, not super affordable. So most researchers can't even afford to reproduce this research. There's also the problem that the search spaces were vastly different, so comparing reinforcement learning to DARTs would be like comparing apples to oranges. Enter NAS benchmarks. NAS benchmarks accomplish the following. They can compare algorithms against a common baseline. They can make NAS research more accessible for researchers with fewer computational resources, because then researchers don't need to spend time evaluating the architectures. Lastly, they can give some insight into the NAS search space. Here's a list of some benchmarks that are popular right now. NASBench 101, NASBench 201, NASBench 301, and NATSBench. The last thing I want to briefly mention is that the NAS I've discovered so far is mainly for image classification, but there are other applications of NAS as well, such as in automatic speech recognition and natural language processing. So, why care about neural architecture search? As I mentioned earlier, neural architecture search makes it so that people who aren't computer scientists, such as doctors, climate scientists, or physicists, can still use neural networks in their work. And not just any neural networks. The neural architectures found by NAS algorithms have been found to perform similar to, or in some cases, even better than, human-designed architectures. Neural architecture search is just one part of this larger field called AutoML. I think this is super cool conceptually because you're often doing machine learning on the machine learning, and it also has the practical benefits of making machine learning more accessible for non-experts. Lastly, you should care about neural architecture search because it's such a young field. That paper that I mentioned that sort of generated all this NAS hype was only written in 2016. This means that there's a lot of research potential in this field, and we'll be seeing some pretty exciting things in the next couple of years. Let's summarize what we've learned today. We learned that neural architecture search, or NAS for short, is a process in which a neural architecture is algorithmically generated or selected as opposed to handcrafted. We learned that some NAS paradigms include reinforcement learning, neuroevolution, DARTs, one-shot NAS, and training-free methods, with reinforcement learning, neuroevolution, and DARTs being more expensive, and one-shot NAS and training-free methods being less expensive. We learned there have been some reproducibility problems due to expensive computational costs and different search spaces, which has been addressed by the creation of NAS benchmarks. While the current research is mostly focused on image classification, there are other applications of NAS, including in automatic speech recognition and natural language processing. We learned we should care about NAS because it makes neural networks more accessible, creates architectures that achieve state-of-the-art performance, is part of a larger field called AutoML, and is a young field, meaning there is lots of exciting research to come in the next couple of years. Thank you so much for watching, and please, feel free to comment any topics you would like me to cover next. Would you like me to cover NAS more in depth? Let me know. I also welcome feedback for how I can improve my videos. As always, this is your CS Professor of Fun.